Perhaps you've seen this brown bottle before, most likely in your first aid cabinet. And what you did is you grabbed that bottle of hydrogen peroxide and you poured it on a cut. When you did that, it would start bubbling like crazy. What's going on there? Well, it turns out hydrogen peroxide oxidizes things. And if you recall, oxidizing means removing electrons. So it's grabbing electrons off of things. And if the thing it grabs electrons off of is bacteria, well, the bacteria isn't very happy about that, and it dies. So that's why it disinfects your cuts and wounds. What we want to do is take a look at this oxidation reaction in this lab. We're going to compare how quickly hydrogen peroxide decomposes when we put it with nothing at all, that's called a control experiment, when we add it to a potato or celery, or when we add it to yeast. Which one of these conditions will cause our hydrogen peroxide to break down the fastest and release all of those bubbles you're used to seeing? Let's take a look. Let's begin by reviewing our lesson objectives. First, we'll introduce the required materials. Then we'll practice identifying oxidation states. And lastly, we'll introduce the lab procedure. So let's get started with those required materials. We're going to take 3 glasses. So you need 3 cups. They don't necessarily need to be made out of glass, but it is nice if they're transparent. So a transparent plastic cup is also great. To each of these cups, we'll add hydrogen peroxide. This can be found at any pharmacy near you or at a local grocery store, generally in the first aid section. To all of these cups, you'll also add dish soap, which is going to measure how quickly hydrogen peroxide bubbles in these different cups. To one of the cups, you'll add potatoes or celery, and it's completely your choice. Either one is totally fine, so you're just given options here. To another cup, you'll add yeast. You can get a bag of dry yeast at your local grocery store as well. So here's all of the required materials that you need for your lab. If you're ready to get started, go ahead and pause the video, go gather these materials, and then come back and finish the lesson. All right, well, let's understand some of the background for this lab. Let's start with the decomposition of H2O2. That's hydrogen peroxide, which comes in that brown bottle. Well, it decomposes into water and to oxygen. And we want to balance this chemical reaction, so go ahead and pause the video for a second and see if you can figure out how to balance this chemical reaction. Well, if we add a 2 in front of H2O2 and in front of our H2O, we'll get a balanced chemical reaction. Now let's add the phases of each part of this chemical reaction. First up, the phase of hydrogen peroxide. It comes in this brown bottle and it will look like a liquid, so it's important to think carefully about the phase here. One thing to keep in mind is that this bottle is just 3% hydrogen peroxide. And it'll say that on the bottle. Most of it is water. 97% of it is water. So hydrogen peroxide is actually dissolved in water. And the phase for dissolved in water is aqueous, which we abbreviate AQ. So I know H2O2 kind of looks like a liquid, but it's actually aqueous, it's dissolved in water. Water, of course, actually is a liquid, which we abbreviate with an L. And oxygen, that's the important one for this lab, it's a gas. So oxygen will bubble out of our solution. And here's the trick that we're going to take advantage of in our lab. Oxygen bubbles will be captured by soap. And so you'll be able to easily visualize how much hydrogen peroxide has decomposed by how much soap you have above the water. The more soap, the more hydrogen peroxide has decomposed. During this decomposition, there's a redox reaction going on. And so let's review determining oxidation states. Let's start with some helpful rules. First up, hydrogen's oxidation state is +1, so remember that. Then the oxidation states for molecules have to add to 0. So if I add up the oxidation state of every atom in my molecule, it must be 0. Lastly, if there's just one element, then the oxidation state is 0. All right, well, let's practice this for H2O2. We kind of set this up like an addition problem with 2 columns. On the left, we'll put our hydrogen, and on the right, we'll put our oxygen. Then we want to assign the oxidation state of our hydrogen. Remember, I reminded you in those previous rules that hydrogen is always +1, so we're going to assign the +1 to both hydrogens. Now, if I have 2 hydrogens, each at +1, those add together to give me +2. Next, we're going to use the rule that the total oxidation state has to be 0 for our molecule. So hydrogen peroxide has to add up to 0, and that means that oxygen must total to -2. If I take that -2 and I distribute it across both oxygens, what would the oxidation state be on both of those? Well, each one has to be -1, because -1 and another -1 gives me -2. Okay, now let's try that same thing for water. So this is just H2O, just a slight difference here, and that's that your oxygen, well, there's only one of them. So pause the video and see if you can figure out the oxidation state by assigning hydrogen as +1 and figuring out what oxygen is. Were you able to do it? It turns out that our oxygen will have a -2 oxidation state. And you can see the difference here is just that when I go to distribute the -2, there's only one oxygen to distribute them across. All right, now let's apply this to our chemical reaction. On the top, we have our chemical reaction for the decomposition of hydrogen peroxide. We have the before column on the left and the after column on the right. And then we have all of our atoms listed. What we want to do is write down the oxidation state for all the elements from all of our different molecules before and after the reaction. So we've already determined that before with hydrogen peroxide, we have +1 for hydrogen and -1 for oxygen. Meanwhile, after our chemical reaction, we have a +1 for hydrogen and a -2 for oxygen. Lastly, oxygen is all by itself, and that's where the last helpful rule comes into play. Because oxygen just has O in it, it's going to have a 0 as its oxidation state. This reaction's a little tricky because our oxygen has two separate things that happen to it. It can either go to water or to oxygen. For the one that goes to water, what's happening? It goes from a -1 to a -2. We call that being reduced. So let's just remind ourselves what reduction is. Reduction is a drop in oxidation state. And when our oxidation state drops, that's the gaining of electrons. So what's happening is our oxygen is gaining electrons. What about our other oxygen? The one that goes from hydrogen peroxide to being all by itself. Well, there it goes from -1 to 0. What do we call that when it increases in oxidation state? We call that oxidized. And oxidation is an increase in oxidation state, and it corresponds to the loss of electrons. Okay, so we're running a redox reaction in this lab, and our big question is, what will cause hydrogen peroxide to decompose the fastest? Let's go over our lab procedure to see how we'll do this. Our first step is we'll place 1 cup of hydrogen peroxide and some soap in each of our 3 cups. To the first glass, we're going to add nothing. That's right, nothing. So this is actually like a careful part of our experiment to see what happens to hydrogen peroxide if there's nothing done to it. In science language, we call this a control. To the second glass, we're going to add celery or potatoes, okay? And to the third glass, we'll add 1 teaspoon of yeast. Then what question we're going to ask is, in which cup does hydrogen peroxide decompose the fastest? And remember that we'll measure that by bubbles. So which cup will make the most bubbles? Let's review what we've learned. We introduced the required materials. We practiced identifying oxidation states, and that's useful to be able to look at our redox reaction and decide what's being reduced and what's being oxidized. Lastly, we introduced the lab procedure where we saw that we're going to compare the rate of hydrogen peroxide decomposition in the presence of nothing at all, a potato or celery, compared to yeast. Good luck.